Hi, my name is Lisa Meine and I'm from the University of Erlangen-Nuremberg, which is in Germany. And it is my pleasure to present you two things in this video. First, you will learn about network calculus and how we can use it in time-sensitive networking. And second, I will use it as a short teaser for my survey, which I published at the ICTC 2020. So, my research is dealing with two main terms, network calculus and time-sensitive networking. Network calculus is a mathematical framework with which we can derive maximum backlogs and delays. Meaning, in the worst case, what is the maximum latency which my packet will experience in a network, and what is the maximum buffer sizes which I will have. And time-sensitive networking is a technology in which we use network calculus. It is a set of Ethernet standards developed by the TSN, short for Time-Sensitive Networking, working group, and it enables Ethernet with real-time capabilities for time-sensitive transmission. So first, I will present you the basic principles of network calculus. Then some reasons why we, or maybe also you, should use network calculus, and at the end I will give you a short overview about the current results of network calculus models for time-sensitive networking, because we have many different schedulers in TSN, and each of these schedulers has different models. So I created a survey in which I highlighted the scope of all models and explained them illustratively, and in this course also found their interdependencies and also some differences. So, network calculus relies on flows, input and output flows, which travel through a system. A system can be anything. It can be a whole network, a router, or only a queue. And we always use cumulative functions in network calculus, which means we plot a time and how many bits already enter the system since time t is 0. So if we would just observe this system here, then we could observe an input and an output flow, which might look like this. And then we see, okay, the fifth bit enters the system at time t equals 17 and leaves it at time 24. So the delay it experienced is 7. Of course, this is not the worst case delay it can experience, neither is it a guarantee. So what we now need to do is find upper and lower bounds for these curves. So for the input flow, we use the concept of arrival curves. An arrival curve is just the maximum number of bits that enter the system, regardless when we start the observation. So in this case here, this arrival curve would not be a valid function for the observed input. And if we have an arrival curve, then we also need to define a service curve, where the main modeling part of network calculus comes in. Basically, the service curve says, what is my minimum service or forwarding capability of the system? And I will show you an example how to define this in time-sensitive networking in a minute. This behavior of the curve is called the rate latency function. Because we have an initial latency for which we do not serve anything, and then we serve the bits with a constant rate. And it's a typical function for network calculus. So we will also use it a lot in the next few minutes. If we have only these two functions, then we use the concept of min plus algebra to derive several guarantees. Do not fear the term min plus algebra. To put it simply, min plus algebra just means that we use a different definition for mathematical operators. For example, we redefined the convolution and the deconvolution. So our definition at network calculus of the convolution is this term and the deconvolution below, and I will explain you what these two terms will mean on an example. Okay, using just the service curve and the observed input, we can get the minimum output of the system by using the convolution. This means that we just take the input curve and the beta, which is the minimum service curve, and then put one of the two curves at each point of the other curve. It is cumulative, so it doesn't matter which of these two functions we use, but we just put it at each point of the other curve, and then the resulting minimum of this is our new curve, which is the guaranteed minimum output. There are two further guarantees which we can derive from arrival and service curves. The maximum horizontal distance between these two curves is the maximum or worst case latency, and for the vertical distance, this is the backlog. And the third guarantee which we derive is the maximum output curve. Why do we need it? Before we had the minimum output, now we have the maximum output. And the maximum output is of course the worst case input of subsequent nodes. So we can just use beta and alpha, and in this case it's not commutative, so we use beta and shift it over the time axis. And then we remember where have we shifted our curve, where has it started, and look, where is the maximum distance between alpha and beta. And this maximum distance is then put at the point where we shifted our curve, and the resulting new curve, the upper bounded, is then our maximum output curve. This can be improved with shaper and maximum service curve, but this would be too much for now. So we just stick with these two curves. So far about the math part of this video. Now, what are the reasons why we should use network calculus in TSN? First, as I already highlighted, we have guarantees. And the cool thing is that we also have them for non-deterministic schedulers, meaning schedulers in which different traffic classes or flows influence each other. And then the delay analysis is non-trivial, and we need frameworks like network calculus to even get delays. Second, we have a reliable and replicable evidence that our network can meet all deadline requirements, which is particularly important in critical networks. And another big topic is that we can support network designers. For example, they can get information about whether their schedulers they have chosen fits their context, or if some packet loss will appear in the network. Since we know the maximum buffer spaces, we can scale our network to prevent all packet loss which would be due to buffer size overflow. Maybe the coolest part of it is the configuration part. We can validate if our current configuration meets all requirements. We can also use more complex schedulers and configurations. For example, in the time-aware shaper, currently all configuration approaches strictly separate flows, so the delayed analysis is simple. We can model more complex configurations and thus increase the solution space of our configuration. And where can we use this? Either we implement it in a central point at the network, the so-called centralized network controller, or maybe also decentralized future work to update the maximum accumulated latency field of stream reservation protocols in TSN. Okay, here we see a small part of the main table from the reference survey. And as you can see, I've included all network calculus models for TSN and sorted them to the mechanisms which they modeled. So as you see, for each scheduler, multiple models exist. And in orange, you see which is the most advanced work. So if you're interested in one particular model, the orange parts should be the first source for lookup. And also I identified how the models depend on each other, how they reuse results from each other, and plotted what do they include, which functionality of TSN, and which curves have they derived. And during this course, we were able to improve the detailed arrival curve of aperiodic traffic, and also identified that the preemption was not homogeneously modeled in all networks. To give you an idea how TSN is modeled in network calculus, I will present you some of the results which are already derived. So, for the arrival curve, the TSN standards defines a strict behavior. For example, if the flow sends periodic, then we have a maximum interval in which we can send at maximum n bits. So to get the arrival curve, we will assume that the packets are all sent as early as possible, since we need a maximum arrival curve, right? So in this case, the arrival curve would look like this, and then after the n bits were sent, no further bits can be sent until the CME interval is over, and then directly at the beginning of the next interval, the next bits follows, and so on. So this is a valid arrival curve for TSN. And in network calculus and to ease calculations, we typically upper bound this with a so-called rate burst curve. For the aperiodic traffic, the curve is very similar. The only difference is that at the beginning we can send a doubled amount of bits, and so this curve would be changed to this function here. And in this case, we were also able to improve the function of the detailed arrival curve, as you can see in the picture. For the service curve, we need to look into the details of the time-sensitive schedulers. So the first scheduler is the so-called credit-based shaper. If you look at a typical TSN output port, ideally we have up to 8 queues, 1 queue for each traffic priority class. And then we can put our schedulers to determine when packets of this queue can be sent. In a credit-based scheduler, we assign credits to each queue, and the credit decreases if a packet is currently under transmission, and increases if a queue waits. For example, because it is not allowed to send, or because another packet is currently sending. A queue can only send if its credit is bigger or equal to 0. So in this case here, even though no other packet is currently sent, we need to wait until our packet decreases to 0 again, and then can send the last packet in the queue. So how can we model this as a service curve? We will first look at the maximum credit of each queue. We will model the maximum credit in a way that once the queue reached this credit, it is guaranteed to send, because it cannot get higher. This is how we calculated it, right? And so we just need to see, okay, how many other packets can send before me, how high will my credit be, and this then makes the maximum latency before I start serving my packet. And then I reserved with the reserved bandwidth, which in credit-based shaper is called the idle slope. If you would look at this in more detail, then of course you would send a packet at link speed and then wait until the credit increases again, but this is typically just lower bounded with this curve. So we can also model that we have higher priority queues than our credit-based shaper queues, but this is maybe a topic for the next video. Heading on to one of the next schedulers. We have multiple schedulers since we can also combine them and then need to define models for this combination. So in this case here, we would combine the most commonly known time-sensitive networking scheduler, which is called time-aware shaper, with the credit-based shaper. And we have gates before each queues, which are determined when they open and when they close by the gate control list. And in this case, we will see that we can just reuse the previous defined curve of the credit-based shaper and adapt it slightly. And this is also the main benefit of the survey, since we see that we do not have different models, but that we can reuse the results of the previous ones and only need to do some small adaptations. So here we can use the credit-based shaper curve and model that it does not send while the gates are closed, and also the guard bands and some preemption phases. But for details, please refer to the survey. So here we saw that the preemption was not modeled the same in all works. One modeled that the credit increases during the sending of overheads. The other one said that it is frozen during this time. So in future, we need to define a unified model to get the real latency which the flow will experience. Last but not least, a new shaper which is currently under definition in the standards, the asynchronous traffic shaping mechanism. And to put it in simple words, the main result for the asynchronous traffic shaping is that we can use it in conjunction with any other schedulers. The delays will not change with the asynchronous traffic shaping or without. So we can just reuse our service curve, which we have defined before, and simply leave it like that, assuming that the traffic is already reshaped according to the asynchronous traffic shaping effect. So to put it together, you now learned a lot about network calculus and why we should use it in TSN. And also you saw the current state of the art. And for details, please refer to the survey, and maybe we will get in contact in the future. I would be happy to meet you. Bye.